please put your attention to the bulk polymerization or manufacture of polymer by bulk polymerization technique. Here is a flow chart for nylon yarn manufacture. Here this nylon which is manufactured by bulk polymerization technique can be prepared in the form of granules, or in that establishment there can be setup or units which can lead to the final product also. Here it shows nylon yarn. From the yarn one can make, from the fiber one can make yarn, nylon yarns. Now, here in this flow, typical flow diagram, see these are the raw materials, raw material cellulose, adipic acid and hexamethylene diamine. Hexamethylene diamine is actually dissolved in water, adipic acid is dissolved in water. When these two are mixed in solution phase, some nylon salt is formed. Okay. Here you see this nylon salt is formed. Actually, that step is not shown here separately in this flow diagram. When these two reactants are mixed, immediately a solid precipitate of hexamethylene adipamide is formed. Hexamethylene adipamide. If you add acid to an amine, say aniline and HCl, aniline hydrochloride is formed, that is aniline salt. Likewise, in this case hexamethylene diamine, when it is mixed with adipic acid, hexamethylene adipamide salt is formed. Now, here this is a condensation polymerization. It needs a strict control of stoichiometry. You have seen, if the stoichiometry control is not properly maintained, one cannot lead to high molecular weight product. You have seen, even if you go up to 99% conversion, you may not get high molecular weight polymer, provided you do not have this 1:1 or equimolar ratios of the reactants are accurately taken. And again, that is a difficult task during weighing of the raw materials, say adipic acid and hexamethylene diamine. These raw materials, during weighing, some quantity of any of these two may be less or more other than equimolar mixture. But if you mix these two in solution phase, a salt will be formed in 1:1 molar ratio, and then that salt is, since that is a solid, that can be filtered and washed, and which can be further proceed to melt polymerization of that salt. Now, if you consider this as a reactor where salt is formed, then that is transferred to another evaporator where water is removed from the solution or it is filtered. Most important thing, is this one, reactor, main reactor, where this polymer gets melted, salt gets melted, and it is maintained at high temperature gradually above 250-60 degree Celsius, and this is a stirrer, this is the reactor, and this is the jacket, this is the dumping side. So, this molten mass is kept stirred continuously for proper heat transfer, then that your polymer molten polymer from this reactor is poured onto a casting wheel. Okay. Means nylon, fully grown nylon solid polymer is cast in the form of thin sheet over this wheel in a continuous manufacture, and that is actually cooled. A casting is done by air cooling on the wheel. From molten mass it becomes solid sheet over the wheel. Then that is actually passed through a mill, chopper mill, which cuts or chops that sheet into smaller size. Okay. So, you will get nylon chips, and then that nylon chips can be used for many purpose, for product fabrication, say for fiber drawing or casting of some structural items like say gears and other things. But if there are installations for fiber drawing, so that fiber that chips are passed through that fiber drawing units, where spinnerets are there. Spinnerets is a device which contains very narrow opening, narrow holes, through which it is this mass, molten mass, or sometimes in solution those are pressurized out of this spinneret, forming very thin fiber. So, thin fibers are coming out from the spinneret, that is cooled by fan, air blowing, and then these are actually passed through some wheels, and ultimately the yarn is formed. Yarn means it is a bundle of fibers, twisted, little twisted. So, nylon yarn is made from this process. The essence of these things is the reactor to which this nylon salt is fed. It is maintained at very high temperature, and the conversion to high molecular weight occurs over here. Then that is the polymer is obtained from the bottom side of the reactor. We get the polymer product. We can get in the form of sheet, in the form of flakes, in the form of granules, etc. Then we can utilize that raw polymeric material for fabrication of molded items or yarn or fiber. Okay. This is a flow chart for the manufacture of polyester fibers. Achha. You know, say As I told you, this PET, polyethylene terephthalate, it can be manufactured from ethylene glycol and terephthalic acid, or it can be made from ethylene glycol and dimethyl terephthalate. Both these can lead to polyethylene terephthalate. Now, this is actually this is the most accepted technique, this DMT route. Here this shows a DMT route. Now, till this point actually this step shows formation of dimethyl terephthalate. Although when we study these polymerization principles, we just show that these reactants like ethylene glycol and terephthalic acid or ethylene glycol or dimethyl terephthalate, they are reacted, and by ester interchange process principle, this polyethylene terephthalate is made. What is what is called ester interchange reaction? Ester interchange reaction. Dimethyl terephthalate means it is already an ester. Dimethyl terephthalate okay. In this DMT, dimethyl terephthalate, this is the ester group and this part is the alcohol part. These are the two alcohol side. Okay. Now, when these alcohol sides, alcohol parts are replaced by what happens? You get okay. Producing okay. Here this is the byproduct, methanol is the byproduct. And this entire molecule becomes a diol. It becomes a diol, intermediate diol or bigger diol. This will further react with this kind of thing, or or it can react with another DMT molecule. Ultimately, what we get, gradually this unit grows bigger and bigger and bigger, by which time methanol is produced. So, this is the simplest way of looking or viewing the synthesis of this polyethylene terephthalate. But in some industrial installation, if you go, you will find huge number of units are combined, connected to each other, one after the other. Now, in this flow, again this flow diagram is a simplified flow diagram. A real industrial installation for PET manufacture may be further complex or complicated than this simplified flow diagram. So, what is here you see, this is a reactor type where this terephthalic acid is actually synthesized. That means, in that installation, instead of buying DMT, that manufacturer, they themselves manufacture this DMT in their own plant. So, in this flow diagram, it shows the production of polyester fiber, PET fiber from your xylene, paraxylene and other reactants. From paraxylene, they prepare this terephthalic acid. So, this is a terephthalic acid synthesis or manufacturing reactor. Okay. Here is a stirring system, it is autoclave type reactor, paraxylene, that as well as catalyst and air, and that converts this paraxylene to terephthalic acid. What is that reaction called? Oxidation. Oxidation. So, paraxylene is oxidized to terephthalic acid. What is the formula of paraxylene? So, this product terephthalic acid, this is manufactured in this container and it passes through certain purification unit operations. In any chemical plant, there are several units having different functions. They are installed and if that production passes through those unit operations controlled by chemical engineers. So, here this terephthalic acid is manufactured and after it is dried, then it is converted to DMT, dimethyl terephthalate, where this terephthalic acid is fed to this reactor, methanol is added and the temperature is maintained at 150 degree like that, DMT is made. So, this is called esterification reactor. And this DMT is crystallized in a crystallizer in another unit. So, DMT crystals are formed in methanol and methanol is separated and sent to recovery, again which can be recycled to, this methanol is recycled to this step. You see, here if some quantity of methanol is used at the beginning, same methanol can be recycled for DMT manufacture. Otherwise, what will happen if your company buys DMT from outside, then methanol will be a byproduct in your unit, then that byproduct is to be sold, otherwise cost competition cannot be reached. So, it is for those regions it is better to manufacture DMT in the same installation. So, some quantity of methanol which is used at the beginning, that can be recycled number of times. There may be little loss, through evaporation, spillage, etc. Barring those things, if we say there is no loss, then this process may become economic. Then it passes through a melter where DMT is melted, then it is pumped. Molten DMT is pumped to for purification, because that may contain some trapped methanol, all those things, because if those are not removed, again that may affect the polymer molecular weight. So, actually basically it is a stripping column, or it may be called other way. Here it is a toluene esters. Toluene ester means a DMT. Then that hot molten dimethyl terephthalate is passed to this polyester reactor, polyester formation reactor, where ethylene glycol is fed. Here also, after this methanol, from this DMT, after this polyesterification, this methanol is, which is produced as a byproduct, this methanol produced as a byproduct, that can be recycled to this step. Now, here the methanol recovered, that is the excess methanol, in this case excess methanol, because this reaction is carried out taking terephthalic acid and excess methanol. One of the reactant is taken in excess quantity, large quantity. So, it gives you higher production, higher conversion, so that it does not set equilibrium. That is why methanol is used in excess. So, gradually there will be more and more conversion to DMT here. So, here this methanol recovered, that is the excess methanol, this is not the byproduct actually, the excess methanol, here is the byproduct methanol, that also comes over here. So, whatever methanol consumed over here, so that methanol is got back here, then polyester is synthesized. Now, if you look into that the flow diagram given in that polymer chemistry by George Odian book, they will find that there are these polyesterification reactors. There are not only one reactor, there may be 3 or 4 reactors, where the reactors are maintained at different temperatures. You will see there. Please see that diagram, flow diagram. Actually, what happened? I asked my assistant to draw this diagram from a book. I did not have time to examine what is this kind of diagram. He made for me, and I found that those reactors are not there. So, in that polyesterification reactor, there may be more than 3 or 4 reactors. Suppose these a series of reactors, in all these reactors PET formation occurs, but the temperature is different because here lower oligomers, medium oligomers, higher oligomers, high molecular weight, because I told you with the growth of size their melting point changes. So, the first reactor may be kept at lower temperature, then the next one is little higher temperature. This way finally, we get high molecular weight product from the last reactor, then it can pass through other units, subsequent units, here you see. So, these 4 in this case, in this diagram, all those reactors are shown in one place. Anyway, here you see this is here also it is shown in a different way, 260 to 300 degree Celsius temperature, and then its glycol recovery is also there, and ultimately we get through polymer chipping system, it cuts into small flakes or granules. Then if it is passed directly to a spinning system, we can get PET fiber. So, in one industry who are making this PET fiber, is a huge industry, because these garments which are we are using this PET fiber, polyethylene terephthalate fiber mixed with cotton, we get terry cotton for garment manufacture. So, they are making these fibers there as well as blending. Or else instead of making fiber, one can install some blowing unit or vacuum bag molding unit. So, these PET bottles, PET containers are also manufactured in the same installation directly from here. Next, let us see polymerization in homogeneous system. So, we have seen bulk polymerization, some installations where different units are involved for getting a polymer granules or flakes or fibers etc., from a homogeneous system, and you have seen the merits and demerits of that bulk polymerization. In a heterogeneous polymerization system or a homogeneous I will come heterogeneous polymerization system later. The solution polymerization is again a homogeneous polymerization system. In order to overcome some difficulties of bulk polymerization, to overcome some difficulties of bulk polymerization, the solution polymerization technique is followed. What is this? Here the monomer is dissolved in a solvent. Monomer may be a solid or a liquid. So, you take a monomer solution in a suitable solvent. Again here also the considerations of this condensation principles and addition principles come into play. In case of condensation polymerization, normally this solution polymerization technique is not followed, because this condensation polymerizations needs higher temperature, because their melting temperatures, melting points are higher than those of addition chain polymerizations. So, in majority of the cases the solution polymerization is followed for addition chain polymers. And characteristics of this solution polymerization, here you see after the polymer growth, that polymer remains dissolved in the same solvent. Okay. The purpose is, in case of bulk polymerization, the entire monomer, there is a chance of entire monomer, or some, not always chance, it is the case that entire monomer gets converted to polymer. So, there is gradual increase in viscosity and finally, it forms a solid polymer in the solid phase. So, in order to avoid the problem of heat transfer, viscosity, auto acceleration, all those things, to control runaway reactions, all those things, people go through the solution polymerization. So, even if the viscosity of the system increases due to the presence of solvent in the polymerization medium, viscosity can be kept at a lower level. Say you take a solution polymerization batch where 70% or more than 70% or 80% or 90% even is the solvent, 10% is the monomer. So, 10% monomer, when there is 100% conversion, so 10% polymer will be there in the solution. So, here the 10% polymer remains dissolved in the solvent, means it is a solution and viscosity of the system is low. And what happens? It helps easy control of the polymerization, because since the viscosity is low, the stirring cannot be so big problem as is found in case of bulk polymerization. So, it can be easily controlled. Not only that, if you can feed a condenser to the reactor, what happens? Due to exothermicity of the polymerization, that will increase the temperature, that will boil the solvent will boil up and go to the condenser, leave the heat in the condenser and comes back after condensation in the form of liquid. Okay. So, suppose there is a condenser like this, So, it is connected to this condenser is connected to this reactor. So, it contains the solvent, temperature becomes high. So, solvent evaporates and goes to condenser, and through the condenser some sorry, through the condenser some coolant is passed. So, solvent gets condensed over here, leaving the heat in the condenser or to the condensing your the circulating medium, and it comes back. So, it maintains the viscosity of the polymer solution which is formed over here, and it provides better control of heat. But here the heat transfer problem is solved, which is a difficult situation in bulk polymerization. In this case, heat transfer problem is solved, viscosity problem is managed because it is low viscous system, and the stirring your power consumption due to mechanical stirring for homogenization of the mass inside the reactor, that huge power consumption cannot occur in the solution polymerization as is found in case of bulk polymerization. But there are certain problems. These problems are obvious. What is the product here? Product is polymer and solvent plus other impurities. Then it passes through polymer isolation. Polymer isolation by solvent removal. In these cases, you see the solvent which is used is an organic solvent. You understand the problem of handling organic solvents in industry. These are highly volatile solvents, sometimes low boiling solvents. Even if there is no leakage from the reactors, pipelines or leak proof system is provided, but we will find the that plant area will be will contain higher concentration of those solvents in the atmosphere beyond this acceptable limit in the environment because of little bit of leakage during purification, isolation, all these things. So, this is not a very good technique of polymer manufacture involving solvent. It causes environmental concern. Apart from that, it is not always possible to remove last traces of solvent from a high viscosity solution. as more and more quantity of solvent is removed by distillation, stripping or other techniques which are available there. The being organic in nature, the polymer as well as the solvent, some solvent will remain trapped, dissolved in the polymer. So, we cannot get a very high pure polymer, we get a low purity polymer product. Cost of this product, cost of this polymer will be higher, because the solvent removal step becomes expensive. If somebody needs very high purity polymer from the solution polymerization technique, that will incur very high cost for purification of the polymer from the solvent. So, cost will be more. Apart from this thing, if we do not need to isolate the polymer from the solution, we can directly use it. Say polymer is manufactured for the purpose of surface coating, paint industry. For paint industry, we can synthesize the polymer by solution technique. So, we will get a polymer solution in a solvent. So, we can avoid the solvent removal step if we can directly use that polymer solution for surface coating or for other purpose, okay, or direct fabrication of the product from the polymer solution. So, it is written here, this technique is not useful for making dry polymer granules or fibers or flakes, or sometimes it can be used for fiber manufacture direct. In that case, it is advantageous. Say for PAN, polyacrylonitrile, for polyacrylonitrile, for polyacrylonitrile, it is a tough horny polymer, and for this polymer there is a good solvent, good organic solvent which can dissolve it. For this PAN, people use sodium thiocyanate. So, what is done? This PAN is dissolved in aqueous sodium thiocyanate. It is a very good solvent for this PAN. It gets dissolved, then this PAN solution in sodium thiocyanate solution, so solvent. This is passed through a spinneret for fiber spinning. Actually, it passes through a coagulation bath. This is a coagulation bath. The fiber gets coagulated, and we get PAN fiber. So, except these cases of direct product manufacture, the solution polymerization technique is not suitable. And in some cases what happens, although the polymer is synthesized in solution phase, in homogeneous phase, it can show initial homogeneity due to solubility of the monomer in the solvent. In later stage, what happens? The polymer, the high molecular weight polymer formed may not be dissolved by the same solvent. In that case, polymer separates out by precipitation. That is a good technique again. Initially, it is homogeneous system. So long it remains in the soluble phase, polymer growth occurs. After certain growth, when the polymer is of adequate molecular size, it comes out of the soluble phase, polymer precipitates out. So, that is also a solution polymerization, but you are getting polymer isolated. It is easy technique, simple technique, and you can avoid the polymer isolation step by solvent evaporation, distillation, stripping, etc. In that case, it is advantageous. At the same time, you are having already the advantages of heat removal, thermal control, control of the polymerization kinetics, etc. If a polymerization is carried out in liquid phase, say here in this case solution phase, since the monomer is dissolved in a solvent, so heat transfer becomes easy and the polymerization kinetics is good. It leads to high molecular weight, avoiding unwanted reactions. If it would have been carried out in bulk, it had to pass through that high viscosity mass, leading to various side reactions. So, including all these things, if you say it gives you good polymerization kinetics, we are not wrong. That means, we can have a better control on polymerization kinetics in this solution polymerization technique. If you have a thermal control, you will have a better control on polymerization kinetics. But the problem is, if we need to isolate the polymer from the solvent, the polymer is less pure than that of bulk process. Okay. Here you look at the flow sheet of solution polymerization process of say polybutadiene rubber. Now, this SBr, styrene butadiene, polybutadiene, PB, sometimes PB or PBr or sometimes BR, same. You will find these abbreviations for the same polymer in different books. Either it is called polybutadiene PB or PBr or BR. The polymer is same, polybutadiene rubber. Now, that this styrene butadiene, polybutadiene or other polymers, they are made by solution process or suspension process. Normally these polymers are not synthesized by bulk technique, they are polymerized by solution technique, solution SBR, solution BR, etc. Their grades are mentioned as solution SBR, solution BR, like this. Now, here you look at this flow diagram. Solvent, as the solvent. Now, the solvent may contain some moisture, other thing. So, that moisture or water is to be removed. So, some solvent, it has to pass through a solvent drying unit, solvent dryer. Okay. Then monomer is fed to the through another dryer. So, monomer and solvent are first dried to remove water, because you have seen if this polymerization is carried out by anionic polymerization, so they need the solvents and the monomers need to be perfectly dried. Trace of water will cause problems in anionic polymerization. So, after the solvent drying, that is fed to the reactor. Here this schematic of a stirring unit is required for homogenization of the mass in a solution polymerization for proper heat transfer, and details are not shown over here. It can have jacketed cooling or cooling coil inside. Inside there may be baffles, all those things. Then the polymer is monomer is converted to polymer containing the catalyst, say sodium amide or other those catalysts are used for polymerization. Then that catalyst needs removal. After removing the catalyst from the polymer, this monomer is removed, solvent is removed, and both these monomers and solvents all are recycled to the silos, okay. Silos are not shown over here. So, this monomer, unreacted monomer and solvent, they are collected from the polymer and recycled for reuse. Then polymer is there. After removing the solvent, it is dried and then it is obtained in the form of sheet, and then those sheets are piled together, large number of sheets piled together in the form of a bale, like bale of cotton layers, like this, bale of garment layers, big bale. So, bales of 50 kg size or 25 kg bales of this polybutadiene rubber, that is collected from this end unit. So, it passes through a baler. Okay. So, we get polybutadiene rubber. So, overall this shows the flow sheet of solution polymerization process of polybutadiene rubber. Thank you.